Going to do a quick overview of the equations, key equations in chapter 9 for linear momentum. So first there's simply the definition of momentum, which is momentum is mass times velocity. So some object moving at some velocity vector has a momentum that's simply given by the mass times the velocity. Impulse is the application of a force over time. So if you integrate the force over time from some time, initial time to some final time, you get the impulse. On average, that means the impulse is just the average force times time. The impulse momentum theorem says that the impulse actually leads to a change in momentum, right? And so the average force could be written as the change of momentum over unit time, or instantaneously, F is dp dt. And if you think about that for just a moment, um, you'll okay, you'll see that if I could write this as let me just get in a new page here. Insert, page break, go back up. Right. So I've got force. Oh, I can't type today. Force is dp dt. All right, and so we can rewrite this as force is mass, well, d dt of mass times the velocity. Right, but if the velocity is constant, I'll put parentheses around that just to. If the velocity is constant, then that mass can be factored out. And so we end up with force is mass times dt, the derivative of velocity. Well, what's the derivative of velocity? The derivative of velocity with respect to time is just acceleration. So we're back to Newton's second law, right? And so at the end of the day, F equals dp dt for any object of constant mass is just Newton's second law. All right, conservation of momentum. Unlike energy, which is conserved unless there are non-conservative forces, momentum is conserved all the time as long as there are no external forces. So the total momentum is going to be constant throughout a collision or throughout a process as long as there are no external sources. And the thing to keep in mind, because this is a vector quantity, that means momentum is conserved in x and momentum is conserved in y. So this vector equation is actually, well, three equations, one for x, one for y, and one for z. And then total external forces equal all the changes in momentum for all different particles. If you got a collection of n particles, numbered 1 through n, you can get the net external force from their change in momentum. If it's an extended object, and by extended object we just mean something that has some volume, then you're talking about the momentum of the center of mass. And so the force acting on it is just the change of momentum of the center of mass. Acceleration of center of mass is just a second derivative, right? And the center of mass is a 1 over m, and m is the total mass. So m is m1 plus m2 plus m3, 1 over total m on to the sum of m1 times r1 plus m2 times r2 plus da da da, all on the top of however many n you have. Acceleration of center mass is just the weighted average acceleration of all the pieces within a collection. And the velocity of center mass is, again, just the weighted average of all the pieces. And if you have to get the center of mass of a continuous object, then you integrate over the object, you integrate over a little differential of mass. The rocket equation, I'm going to go back up in the text. I want to go back to here. table of contents. I'm after chapter 9, rocket propulsion. Look at that a little differently, because when we're talking about rockets, the equation in the summary leaves out what's going on if there's gravity involved. So let's go down to here. So the change in velocity of a rocket is the velocity, this u here is the velocity of the exhaust from the rocket. And then this is log of the total mass before you, or the total mass at the beginning of firing the rocket, divided by the mass at some time later, delta t later, after you've spent some fuel. And so the log of the mass ratios onto the exhaust velocity gives you a change in velocity outside of gravitational field. But there's a gravitational field working against you, and i.e. if you're trying to lift off from the Earth, then this term also applies, minus g delta t. And so the total change in velocity is a combination of what's going on with the mass and the exhaust velocity, and then subtracting out what gravity does to work against you on that. All right, and that's our overview. Hopefully that helps, and we'll get on to the problems.